Thank you, Emily. Hello, my name is Daniel Nenny, and I'm the founder of SemiWiki.com, the open forum for semiconductor professionals. Since going online in 2011, SemiWiki has registered more than 200,000 active members. If you're not a member of the community, please register as my guest. I hope to see you there. Today's webinar is titled Accelerating Semiconductor Design with Generative AI and High-Level Abstraction. The speakers today are Mike Fingeroff, Chief of High-Level Synthesis with over 20 years of experience in hardware design automation, focusing on machine learning and early performance modeling using System Verilog, System C, and MATLAB. He is also the author of the High-Level Synthesis Blue Book. Alan Klink is co-founder of RDA and a technology leader with expertise in high-level design and AI ML frameworks for verification. He has driven innovation in verification and low-power technologies, helping teams enhance efficiency and performance in modern, complex designs. And we have Ellie Burns, currently serves as the head of marketing at Rise Design Automation with over 30 years of experience in semiconductor and EDA industries. She has held diverse roles in engineering, applications engineering, technical marketing, product management, and senior leadership, specializing in driving business growth through strategic marketing. If you have questions, please use the chat box and we will answer them during the Q&A. A link to the replay will be sent to you after the webinar. Okay, let's get started. Over to you, Ellie.
All right, thanks, Daniel. Let me go ahead and start my slideshow and make sure everybody can see it. Okay, can everybody see that okay?
Yes.
All right. Okay, so welcome everybody. Again, thanks Daniel for both hosting this and a great introduction. So today's seminar is Accelerating Semiconductor Design with Generative AI and High Level of Abstraction. We've done a couple of these already, so if those of you that have attended with us before, there'll be a little bit of repeat material and a little bit of new stuff. And so in general, what we're going to do today is I'm going to, as the marketing person, I'm going to give you a little bit of an intro, kind of set the stage of some high-level value statements and things that the tools do, and then I'll turn it over to Mike to step you through, dive into a little bit more technical detail on what we mean by raising the abstractions. There's two pieces we want to cover today, is making sure you understand what we mean by raising the abstraction. And then we're going to spend a majority of the time on the generative AI solution that we have. And we'll turn it over to Alan to kind of take a deeper dive into that. And then at the end, we like to try to give a live demonstration so you can really see the tool in action, understand how it interacts with the high-level design and the user. So let's go ahead and get started. And again, I can see the questions while we're running, and all of us can either type, so please feel free to ask questions at any time during the seminar when it pops into your head. We may answer it interactively, or as Daniel said, we'll make sure we answer it at the end. Okay, so just to set the stage a little bit, you guys have probably seen a version of this slide several times, but we have seen, I've been in semiconductor design a long time, and we're seeing almost unprecedented growth, which is really exciting for the industry. We're seeing, it's driven by, digitalization and everything. I think I've seen lots of different words in different industries that we've seen, but adding smarts and intelligence is needing new hardware, needing new semiconductors. So we're really seeing also the end of kind of traditional CPU acceleration. So the whole idea of your CPU getting faster and faster and faster, that has started to level off. And so we're starting to see the need for very specific accelerators and application spaces to make sure that it fits performance and latency, and most specifically power for the application at hand. Also, I know that we've had a lot of, things like new IP and new methodologies, but fundamentally RTL has not changed in decades, right? So, once it kind of came out and we figured out what the synthesizable subset was, the fundamental things in RTL haven't really changed. But the designs are getting bigger, the time to market is staying critical, and we are seeing from a lot of the customers we're working with, starting to see real shortages in engineering around RTL design, architecture, and basically hardware design. So it's getting harder and harder to hire the kind of staff it needs to do these kind of big projects. So a change is needed, and there's a lot of companies that are talking about this, to meet these short cycles. It's not just a little 10x or 20x in simulation performance that needed, and orders of magnitude are needed in productivity in order to achieve what's coming in the next few years. So with that, I want to dive into what it is that we are doing. And what we're seeing right now, we're seeing a lot of AI and generative AI that's helping, with software development and and all these things. It's crazy. I'm sure all of you out there use ChatGPT to help you write things and answer questions and things like that. But we've seen a little bit of a slow uptick in having that help you generate new hardware. So one of the things we're seeing in our solution is if you raise the abstraction, combine that with a high-level tool chain and generative AI, it's a very, very powerful combination. And we'll talk a little bit more about why it works that way and why that is so powerful. Because you could then apply the AI, but you still have to have a human in the loop and develop high quality, high Q of R, verifiable and implementable RTL. So you have to have that as a minimum and then combine that with the productivity of AI. So that is really what we're doing and what we're going to talk about today. Essentially what we do, so this is just, Mike will dive into a lot more detail and so will Alan, is we have a unique solution for hardware design. So we start here with System Verilog, a high-level System Verilog, or C++ or System C. So you can use any of these three languages in what we call an untimed or loosely timed. And Mike will explain that. And that is the input language that the user writes. Then the tool chain with a human in the loop and technology libraries delivers high quality RTL. And then that RTL goes into the rest of your traditional tools and synthesis, simulation, and everything. So it's readable, it's modifiable, but that is what we're doing. And with that, we are using generative AI. We have very fast synthesis to get you from this high level into RTL, high level verification, and then a full debug and analysis and exploration tools. So again, we'll step through and show you what those tools look like and a lot more detail on what we mean by untimed and loosely timed language. One of the things that we're also seeing, because we support a true multi-language mixed abstraction. And what I mean by that is in your overall project, you can have some blocks in RTL, some blocks in C++, some blocks in System C or high level. You can mix and match those. And so with that, it enables basically a lot of different things for different people that are part of the team, and it allows us to bring together various players that really are kind of separate in many ways. So in the system architects, they can have an executable model of their functionality, and most importantly, look at early performance analysis, which is really important for these, especially for some of the new accelerators, all of this very complex architectures. The RTL designer, he just needs to be able to do things fast, have a reference model, to be able to add features and functionality quickly as specs are changing. Verification engineer, they can start much earlier as these models become available, so you don't have to wait until the RTL is done. You can start when you have the interfaces and the behavioral models. And one of the things that we're doing is that we are keeping the verification in System Verilog. So we'll talk some more about that. And then the software engineer is always looking for basically a virtual platform. And virtual platforms have been around for a long time, but sometimes the models can get out of sync if they are not actually the models for the hardware. So in this case, the virtual platform and the actual model that's going to become the hardware are the same. And so they don't get out of sync because that is that real hardware. Kind of second to last here, I wanted to just highlight on verification, and we will have another webinar that's deep dives into verification. On this one, I just want to explain the concept, which is verification is one of the biggest values you get for raising abstraction because it improves the simulation speed. I have here 30x to 1000x. I thought I'd explain that a little bit. Here is RTL. The 1000x comes from if you make the whole design in C++. This is kind of what you see where your simulator is basically a C++ compiler and everything is untimed. As you move down, we have support for basically a threaded C++. You can do things in parallel and system Verilog untimed. So basically that level of abstraction where you can test the functionality, move down into what we call mid-level system Verilog and system C. So it's loosely timed. Mike will talk about that. So this basically, you're using the same simulator that you already have. So whether it's your system Verilog simulator or your C++ compiler, it's dependent on the level of abstraction. So if you take away things that are happening in the simulators get a whole lot faster and still have the functionality into them. So that's what we're seeing for being able to shift left both verification and make it happen much, much faster. And lastly, just a quick introduction, and Alan will do a whole lot more details on this, is we have incorporated an AI solution. So wrapped all of this with the AI solution, which enables basically the human in the loop to do the job so much faster. It's going to generate quality design and verification code from natural language. And Alan will talk about this, but because we've raised the abstraction, now we can use pre-trained LLMs that have been trained on millions of lines of C++ and Python and C. All of that is a really good foundation for being able to generate high-level design and letting then the tool be able to turn that into quality RTL. So we don't need RTL training data anymore, and that's kind of one of the sticking agents for not being able to be able to use a lot of AI in hardware design. We have specialized agents. Alan will talk a whole lot more about that, and a unifying orchestrator that sits on top of that then takes that and makes it so that it can understand high-level design and high-level tools. And then lastly, we are using as we have here, the high-level tool chain in the loop. And so if the answer isn't coming from the model, this orchestrator and tools in the loop can then interact with the human and interact with the tools in order to get more data, in order to be able to get better answers. So I think it's a very unique solution that combines the human expertise with the tools with very powerful LLMs and data. Okay, so I think there's a couple of questions. I'll try to answer those as we go. I will turn it over to Mike to take a deeper dive into high-level synthesis.
Thank you, Ellie. Let me know if you can see my screen.
Yep.
Yep.
Okay, so this is going to be a pretty brief, just kind of overview of the language and the tool, and it's good. I'm going to try not to cough too much because my allergies are quite bad today. So this is ideal that I'll just talk a little bit about things, and then we'll get into the real meat of the presentation, which is the AI stuff. So for those of you that are familiar with HLS, you've seen this before. For those of you that are not, if you want more details, you can find it on our website. But what does high-level synthesis do? So first and foremost, it can convert untimed or loosely timed system Verilog, C++, or system C descriptions into synthesizable RTL. So the key here is that RTL is automatically generated. So if you have a good high-level description and you've really tested it to get the functionality that you want, you're going to get that in RTL. So it eliminates the ability in a manual RTL design flow to inject bugs into the hand-coded RTL. So you're always going to match your golden model, which is the synthesizable model. High-level synthesis automatically times the design. So it automatically inserts pipeline registers in order to meet your clock frequency constraints based on your target technology. So it's doing auto pipelining, something that can be very challenging when you need to re-architect something if you're doing this by hand. Uh, it adds data flow control. So the interfaces that we'll look at are transaction level interfaces and the high level description that becomes synthesized to data ready valid protocols. And what this means then is that the interface control logic is going to be plugged into the pipeline stall control. And so again, you're going to focus on functionality, not writing low level code to ensure the data is synchronized. You get to explore parallelism. So you can apply high level synthesis constraints to explore things like loop unrolling or pipelining. And this allows you again to tune the performance of the design to trade off area versus performance, and do this all from a single design source. And then one of the other very powerful features is that the tool is able to infer memories or registers from arrays in the design. And the beauty here is that when you start to have complex memory architectures and you're coding your design where you've got arrays that you expect to be inferred into memories, that the memory hookup is automatically, the tool is automatically synthesizing address data and control based on a memory library. And so again, it's going to get it right the first time. There's no guesswork. So what does the language look like? And these are very simple examples, but it's worth just kind of touching on it to see what the coding style looks like. One of the things I won't get into is the kind of there is good and bad coding style for high level synthesis. And when Alan talks about the AI, he's going to touch on how the AI agent can help you understand how to code for the specific language that you're using. In this case, let's just look at the languages. We have untimed C++. We have untimed or loosely timed system Verilog, and we have loosely timed system C. So for untimed C++, what you can see is it's really a transaction level description where there's no clock and reset. We have read and write transactions. These are our streaming channel interfaces that are going to be synthesized to data ready valid protocols. And then within the body of the design, I'm just doing reads and writes on my channel interfaces. And then I write very abstract behavioral code. And I have the option to apply high level synthesis constraints either as in a constraint file or as pragmas to say, in this case, start to unroll this loop. Do, one multiply at a time or two at a time, or do them all in parallel. For the loosely timed descriptions, if we look at the system Verilog example, here we have a module. So this looks very much like the Verilog and RTL designer would write. We've got clock and reset, but we still have these transaction level interfaces. And again, when these are synthesized, these are going to be synthesized into data ready valid streaming interfaces. Within the code body itself, I define a clock process, which allows me now, because I have access to the reset, I can define a reset action. In this case, I'm resetting one of my state variables, but you can do whatever you want. Otherwise, we execute the design. Now, what this means is in simulation, this is essentially executing this algorithm right now once per clock cycle. It's reading the inputs, doing the accumulation, and writing the output. But when I synthesize this, I get to decide how much parallelism am I going to use to implement this multiply accumulate. And ultimately, when the hardware is constructed based on those constraints, it's going to allow me to change the throughput of the design where I could either be reading and writing every clock cycle or every two clock cycles and using, either more or fewer multipliers. And so this is a very powerful coding style because, again, I don't have to worry about the low-level details of flow control. I can focus on the behavior. In terms of the tool, the features of HLS, as we discussed, we get to automatically create RTL, and we can create either sequential or combinational RTL from a high-level description. We use constraints to do the exploration. So the various constraints allow me to explore things such as parallelism, pipelining, and memories. We perform technology-aware optimizations. So libraries are going to be characterized based on your target technologies, and we're going to get that information and use that to pipeline the design based on the clock frequency. And then there are some very advanced optimizations that we can enable that allow us to do feedback-driven optimizations, such as on-the-fly characterization for improving estimations of the various operators used to pipeline the design. And in addition to that, we can also do critical path optimization where we can crunch the worst case critical paths in the scheduled design and back annotate that information into the pre-scheduled data flow graph, which ultimately what this means that allows us to shrink the number of pipeline stages for lower power and smaller area. The tool can be run completely in command line, but also it has a GUI that allows you to do analysis. This allows you to quickly identify issues across the various design stages. You have full visibility in terms of the transformations from the high-level design to the RTL, including cross-probing. You have ways to analyze where we let you look at the Q of R, either table views within the GUI or text files, views to view the schedule design and the pre-scheduled design. And we also can view number of pipeline stages, control flow graphs, resource sharing, and things like that. So just to reiterate then, why are we even talking about this? Why do we care about using high-level design tools, high-level synthesis? Timing closure is automatic. So again, once you've crafted your code, ideally, as we'll see with the help of our AI agent, you just change the clock frequency and the target technology, and the tool is going to repipeline the design in order to give you something that meets timing. Data flow control is built in. So you're focusing on the algorithm and the architecture of that rather than the low-level details of writing state machines to control data flow. That's all control, or that's all baked into the interfaces. You get to explore parallelism and throughput as a design constraint. Designs that have memories for complex memory architectures are quite simple because now you're just using arrays within your high-level description. And then verifying the behavior and the timing ultimately becomes quite easy. And lastly, then now we have a set of reusable designs, essentially reusable high-level IP that you can now retarget to different target technologies and clock frequencies at the push of a button. And that is the overview. If you want more detailed information on what HS really does, feel free to check out the Rise website.
Talking about pushing on a button, let me see if I can push a button here.
Thanks, Mike. Mike, I've been answering questions for you in the chat that you might want to take a look at to see if you want to answer them live at the end or just add to my explanations. So
will do.
Yeah. Okay. Are you ready to go, Alan?
Yeah. Do you see my slides?
I do.
That's fantastic. Hello.
Okay.
Thanks for that. So let's talk a little bit about the stack and the tool chain we have. From day one, when we started Rise, we wanted to build a high-level abstraction tool chain that is AI aware. And it means that for us, the entire stack has been connected and architected such that generative AI is built in from day one. So all the tool chain that exists can truly be connected and is connected through this stack of generative AI. If we take a look at the very, very top, Mike talked about the development environment, the IDE. We have an extension that for VS Code that helps us basically analyze the design, interact with the design, interact with the agents for design optimization. That is all done in VS Code. We can also manipulate this in Python. It's a Python-based tool chain. They can also execute this in a shell. And as you can imagine, by having this modern architecture, we can go and customize and integrate to the nth degree, which is what we're doing and what we have. And the reason why it works is because of the architecture we put in place. Mike talked about the language support, the high-level optimization, and so forth. So I will not go into the details of this. The tool chains by themselves has very clear separations of concern, which means for every point in time, there's a textual report, there's textual data that then therefore can be used for your analysis or for agent analysis. And because of this tool chain, things are fluid, very agile environment that helps us provide you the expertise and the optimization tooling that you need. So keep this picture in mind as I go and double click into the different aspects of what does it mean to have hardware-aware generative AI in year 2025. So for us, generative AI comes in different aspects. It's the aspects of how can I use the knowledge and have an interactive section with an advisor, a chatbot. I am sure all of you are using different kinds of chatbots today to solve different things or experience the knowledge that exists for writing patterns, for coding patterns, for advice in general with reasoning models. You can go absolutely crazy, which is good. The challenge with language models in general, as I'm sure you're seeing, if you ask about things that it's not knowing, it starts to basically hallucinate. It starts to come up with solutions and answers that has no good ground meeting. So the way we work is we have the ability to plug in any language model that you trust and you feel comfortable with, and which are great because now you can talk to that language model in whatever way you want. But in pseudocode, you can define your specifications, you can ask your questions. We ground the language model in our knowledge base. So we, in addition to the language model that is already trained for all things such as why the sky blue to whatever is current today, we ground the knowledge into how do you really design designs? What is the notion of timing? What is the notion of area? Language models are very good at creating code, but they're not synthesis tools. They do not know what the implications of parallelism is. They do not know area implications. They can create RTL and code in no order, either automatically or semi-automatically, but they are not aware of best practices for design because they're not synthesis engines. Because we have an extremely efficient tool chain and because we have shared knowledge as a rack-based approach, if some of you are already building AI framework, you would know what that is. If not, let me know and we have a talk about that. I will go a little bit more into the details on how we have architected and the trade-offs on why we did it this way. The beautiful thing with a language model and the knowledge base is that you're grounding and you're removing as a stretch. You're reducing the hallucinations that can otherwise show up because you are telling the machinery what is right and what is wrong. And that gives us the ability to create good quality answers, which I will show you in a second, on what does it really mean to create this, get feedback on the design itself. In addition to having somebody with the expertise on creating or automation, the creation of design, we have agents that can help us answer questions such as, how might I actually optimize my design for an area of this, or the performance of that? These answers is of course not known to a language model. So how fast would your design run? How would it know that? So to help the tool chain to understand the actual numbers for your design that you might ask for, we have the agent that is calling the right tool chain such that you get correct by constructing RTL. And this is where you will get your actual numbers for the synthesis run that is being doing. And that therefore in turn is helping you to get a loop where you are optimizing the design for a given specific target, which I will show you in a moment. Now, when you have the ability to create code and build details analysis on top of that, there's an agent to call this tool chain in multiple permutations. These agents are used for orchestration of other agents. It's used for correlating and coordinating agents to search for parameters. And we are finding that these agents, our agent is extremely good at finding global optimization or global minima optimization, such as optimizing your design for memory, pipeline depth, and so forth, as Mike talked about. This feedback loop is extremely powerful, and I will show you how it's working. And it basically applies reinforced learning and hyperparameters, if you know from other AI frameworks, to basically search for the perfect optimization of your design based on a given goal. So keep this in mind as I go through the demonstration in a moment. But being conscious of time, I will skip the slides about the code generation and rather just show you how we can interact with a chatbot and create design, just for the sake of it. The way that chatbots are working, it goes through, in our case, a VS Code extension. You can even do this in Python if you want to, on a command line. It will interact with machinery that goes through built on top of the knowledge base. The knowledge base is providing best practices such as coding standard, design patterns, coding patterns. What does it mean to do high-level design? What does it mean to do high-level verification? What is the implication of writing code for area? The implication for writing code for design, for performance? Documentation, libraries. What does it mean to have fixed points? How do you control a library? What are the parameters for calling a library? What are the rules, etc.? The integration itself, as Ellie talked about, we have multiple input languages. So based on the language, we will funnel the right knowledge out of the knowledge base, and we will send that to the language model that you trust. Language model and trust is something that you need to establish, and different people have different rules and different levels of confidence. Some people have confidence about working with a language model in a cloud. Some people do not. Some companies would like people to do the inferencing locally. In the example that I will show you in a moment, I'm doing the inferencing on a consumer-grade GPU here in my office, and that gives me the ability to simply just work with myself, my GPU, do the inferencing, and I'm in a closed environment. I don't have to be concerned about what's going outside the firewall of my company or not. We work in a cloud-based environment, both on Amazon and Microsoft, and we'd like to thank both of them for making that happen. We do not record or share or train anything on what you do. Our knowledge base is our knowledge base, and it's being used as an aid. So there's no feedback mechanism. Some people have been concerned about other approaches where training is being done and who owns what IP. We do not do that in any way, shape, or form. Because in our example, we have found very good use of smaller language models, unlike the very large language models that consumes a lot of memory and therefore leads to very high-end GPUs. We get very far with smaller language models, and as I said, that gives us the ability to deploy it on consumer-grade GPUs. We don't need fancy NVIDIA cards. In this example that I will show you, I'm running on NVIDIA 4090, which is a $2,000 GPU compared to maybe an H100 that might be 10,000. And we don't have a lot of those, so it's easier for us to work on smaller inferencing machinery. So based on the prompt you're asking, the prompt will be sent to the language model that will then either go on reasoning about the information it has or the information that's been provided. Or if you're asking what is the area of my design, it will actually have a function to call the Rise toolchain, and based on that answer, give the information back to the user. And that's what I would like to show you in a moment. So keep this slide in mind. It will be easier to understand what's happening behind the scenes. Because of the stack we have, we can create very efficient tool chains. And as we said, for us, speed is a first-class citizen. We take this very serious. So we normally get from a high-level representation to RTL in a minute or seconds. We have this notion of plug-in. So if you want to have a toolchain where you have more fidelity and you don't get any late-stage surprises after high-level synthesis has been done and you're digging into maybe gate-level synthesis or even place and route, the toolchain is architected such that you can get a feedback loop at any point in time from the high-level synthesis to the RTL, or for the high-level synthesis to the gate level or into the GDS. I put some examples here on if you have in this example, we are hardening a language model with weights, and we use the Rise backend for HLS for ML to create from a TensorFlow into C++, and the C++ in this case is around 6,000 flops and around 500,000 RTL cells. That runs in around a minute to get the RTL, and then it runs 3-4 minutes to gate, and around 10 if we do the initial placement and routing, which is nice because that way I get any late stage surprises that I will normally find in a design flow. I get them right away after 10 minutes, so I can get the architecture to be perfect. So I know I can actually implement my design as well. Likewise, we do the same approach for verification. So the validation aspects is also being incorporated, such as latency and throughput. And for us, power is also a first-class citizen. So based on the use case you're measuring, the power estimation will be added as the metrics. And as you can see, we're now starting to have a tool chain that gather metrics, can control metrics, which means that you can build really intelligent flows where you can do design space exploration and optimizations completely autonomously. Let me show you an example in a moment on how we use the notion of studies, where we're simply defining what is the goals that we would like to have, what might be the parameters I can adjust, even at the high level, for me to go and search this black box space from C++, or in this case, from a TensorFlow to GDS, and start to learn by the machine, by the agent, such that it can find the perfect implementation, the Palero front for the analysis. I'll show you that in a second. But let me see if I can get the demo going and we can talk about it. So again, just a little bit of a brief overview. Can somebody confirm that the VS Code is visible?
Yes, I can see it.
So as I talked about, for us, a chat could look like this. We like Cody. Cody is a plugin that we use to coordinate with our backend toolchain, right? The knowledge base and the path into the language model. Here's a simply loosely timed design in System-Alloc that Mike talked about. These are just predefined prompts. I could just as well type them, but if you know me, it's better to not trust my typing skills, but my clicking skills are good. So I created predefined prompts, and I find these predefined prompts are super helpful for myself as well. Here's the methodology. What is Rise methodology? If you ask ChatGPT about it, it will say, I have no idea what the methodology is, but this is our methodology and recipes on how to be a good chef for design. I can ask it, how do I make my design synthesizable? I now have an expert that helps me understand how can I really go and create a good structure? What are the things I need to keep in mind? It's, of course, aware of what my design can do, such that I can go and make it relevant for example, Mike talked about the streaming channel, the AC interfaces. I can make it generic, or I can ask it to be very specific, and it will generate code based on my design that I can simply copy and paste. I could also make it very specific for my example and use a very specific prompt that is asking for how I can use my how I can change my design itself to be streaming channels. Just a different prompts with different objectives. In this case, I can simply do copy and paste, and now I can run the tool. Many of us might say, well, I could just build a run and it will look up the documentation, but we don't need to do that because we have the ability to just call the tool, right? So I can say, analyze my design, use a technology, and it will use the toolchain we talked about, where it will call the Rise toolchain and let you know what the area and the implications are. And from there, you have log files, you have the RTL that is creating, you can do the analysis of the design, you can start to figure out what is really the report, what is really my summary, who area is a problem, but how on earth would I make my design smaller if this is not what I expected? Here I'm using 32 multiplies because I have 32 But what if I want to reduce that? How on earth might I do that? So I can optimize. I can ask the chatbot for advice on how to optimize the design. So for example, I could do partial or full unrolling. Copy that in. I find that I use copy and paste so much that I created a keyboard macro to do it. What if I want to add an extra interface? What if I need to get the read? If I want to have the, what is the bit we want to, I can optimize. Oops, I can create. Just run this again. I rerun the design with the constraints on the unrolling. But what if I want to make it smaller? Sorry. So here it talks about if I want to optimize the area to be smaller, I can optimize it for the loop bounds. I could use data types. I could do partial unrolling. I can ask it to do the partial unrolling for me. Oh, I could do control it with a partial unroll. I rerun, synthesize, call the agents. It will optimize my design. I now have smaller area and I can continue the path. I could ask it to generate properties. Language models are very good at understanding spaces, data types, copy and paste. You might say, well, Alan, that's great, but for me, verification is actually a problem. I'm a verification guy, and I spend so much time creating verification infrastructure. So having help to create meaningful test cases based on my design, with channels, with instantiations, it's a lifesaver. I spend a lot of time doing this, and I save a lot of time not doing it. One could say, well, why wouldn't I just do it with a UVM? It can generate UVM sequences in the same way. Those of us that are purists are thinking, well, that's just great. But actually, for my example, what I really want is just to have a specification. And once I have a specification, I actually would like to generate the infrastructure for this. And likewise, you do the exact same thing, right? This specification on a matrix multiplication, I actually use the agent to write that. But I could, again, just ask it to generate from the specification, generate the design and generate the test. I hope you see where this can go in terms of automating some of the trivial tasks that we do as engineers, but keep ourselves in control on what is it we'd like to go and do. So we spend more time thinking and less about how we need to implement all of this. Let's see, I get a good implementation of a multiplier in C++. I get a test bench that is working. I reference in my prompt, I don't know if you saw it, I reference specifications in my test plan that is getting implemented. Cover groups, assertions, expectations, all of this can be totally automated because of the infrastructure that we have. I'd like to show you another example on how we can use the agents to call itself in a slightly different way. So imagine that you have a design like what we just have, but we are controlling the unroll factor. So instead of having fixed, we could explore how that might look like. We have a test bench that will exercise this test bench we created before. The UVM test bench that was creating, it's a little bit more verbose. I have a simple wrapper that is simply calling the Rise toolchain with some defines that happens to be the unroll factor, set that to a sequence. And that will then create different variations of this design as it goes and explore it. It's currently running here on my machine. And you see it, we get run times in less than a minute for the different variations, right? We see the clock frequency, we see the power, we see the stack. Each of them are running in the sequence. While this is nice, it gives me the ability to understand what is really the space that I can change the architecture from. In a moment, it will be done. I see that's one task back. And then we can load the design and to manually explore how the architecture is changing as we are looking at the different aspects of the design. So let me show you. So we have an exploration report where we see the different unroll factors. So as we are adding parallelism to the design, different depth, different registers, but this report is interesting because now we see, split this up. I mean, don't you just like VS Code? Where you can look at the different metrics, high-level design, how area is changing, how pipeline status, how throughput is changing over area. As you can see, when you have small throughput and a high throughput, then things are rolled. As you start to unroll, you get more and more efficient hardware. So based on the objective for the design, you pick the right one. While that is nice, if you are like me and you search for constant efficiency, you could create this study, right? You have an architectural study, as we talked about. So instead of me searching for it, I let the machine find it. So I can have a study where I define my clock, my area, my depth, the parameters I can change with, the optimization efforts that Mike talked about. And then I simply just instantiate that study in my Python code, let it configure and let it run. I do 42 trials at the same time, but I do batches of 4. So the loop that is run in 4 batches. I learn from that and run another 4 batches, and I continue for a maximum of 42. I can run that. It will then search. I can analyze the result. I have my study. The study is being updated as I'm searching. It goes through that loop and constantly optimize. Let me show you. This loop constantly optimize until it feeds the right result, and I get the different points in time on where it's searching for the perfect optimization based on my objective. I can go into endless data analytics, see the path we took, how the machinery was finding different sample set. It was searching in this black box, the path as it went there, give me some analytics helps on understanding how it was been and how it was concluded. I could, of course, change it such that, where's my VS Code? I'm searching for VS Code. Oh. I could, of course, change it so I could change the architectural study and go all the way to place and route and simply start to add more metrics such as power, latency, place and route area with the same parameters. I can enable open road. I could change the die area. Simply, they will run longer, but the approach is the same. So based on what I'm searching for, I can have a feedback loop by the agent itself to go and optimize my design on a very few parameters. I know we're running out of time. I have so much more to show another day, but I will give it back to you, Ellie.
Yeah.
Okay. So again, in summary, I will stay on. We really are seeing that this whole idea of AI plus abstraction is going to, and we've tried to give you a flavor for what that means, is faster, higher quality RTL. There's been a couple other questions around the quality of the generated RTL, and we'll absolutely get to that because it's a fantastic question compared to doing this by hand, how much you need to be able to get that quality. We use the Rise AI solution uses natural language to make basically high-level design faster and easier. So all of the things for learning it, all of the things for getting the code right, structuring it, understanding how HLS and how to optimize it, right? So that's been part of the difficulty with raising abstraction is it's not commonly known how to do it. So how does a person quickly come up to speed and be able to generate good high-level design code, because there is bad high-level design code, just like there's bad RTL. So this is one of the things that's very good at making this faster and easier. And then lastly, as Alan showed, now you can take this even farther and do rapid implementation to get this kind of intelligent exploration to be able to make those designs, design decisions that are at the architecture where they need some information all the way from the back end in order to make really good decisions. Now you can have this feedback loop with the speed of these tools to be able to really make those intelligent decisions. Okay, so why don't I stop sharing and stop the recording. And okay, so just a quick thank you for everybody coming. I will make this webinar available in a recorded session. And if you want to hang on and listen to more chat and have some more questions, we'll stay on for a bit more. But I'm going to go ahead and stop the recording. And thank you for attending.